Three, two, one. We are talking about momentum today. So, coming from where we've been, right? We talked about everything velocity. Now we're going to talk about mass with velocity and how that's different, how things will change. So, first up, it was a scientist, Rene Descartes, who's also a great mathematician. But Rene Descartes is going to be the one that comes up with this idea of, okay, I know if something's going fast, that's important. But what if two things are colliding? If two things are colliding, it's not just going to be how fast something is, but it also has to be something to do with how much weight an object has behind it to see what's going to happen to it. So he called it the quantity of motion, okay? And we haven't talked about inertia, but it's very similar to the idea of inertia. When something's moving, the more mass you have, the more inertia. The more mass you have, the more momentum you're going to have. All right, so the first thing you need to know is a formula, P equals mv. P is the letter we're using for momentum. Why not m? Because m's already taken with mass. So we have P is the letter for momentum, m is the letter for mass, and v is the letter for velocity. P equals mv. The equation, or the units rather, are going to be nothing fancy. So if you think about it this way, Isaac Newton, he was really important. So, and he studied force. So when they gave him units, they gave the units of newtons to force. We have James Watt looking at power. So the units for power are watts. Rene Descartes, for his hard work with momentum, he got the units kilogram meters per second for momentum. So there you go. Okay, but it's just going to be the formula. So the mass, the formula, or the units for mass are kilograms. The units for velocity are meters per second. So we'll just say kilogram meters per second are the units for momentum. Okay, some short examples of P equals mv. Think about you on your bike versus a big truck. What's going to happen? Well, obviously, if the two of you collide, the big truck is going to win, because even if the big truck has very little mass, or very little velocity, it's going to have a really high mass compared to you. So the truck will win every time. All right, a school bus. School buses do not have seatbelts, okay, or most school buses don't. And one of the reasons they don't have seatbelts is there's so much mass behind it. When you're driving a school bus, if you collide with something else, there's going to be very little change in velocity. Think about massive velocity. There might be a bit of a change in the momentum, but a very, very small amount of change in the velocity, and that's why there's no seatbelts, because it's got a whole lot of mass. When you have a school bus full of kids, that's a whole lot of mass. All right. When I used to coach freshman football, and freshman football players would be you'd have somebody that has to tackle. We need to teach them how to tackle, right? And you think about what's going to happen. You got a freshman football player that might be this tall tackling somebody that's this tall, right? So what they would do is if they were kind of scared to tackle, they'd be nervous, they'd fall back, they wouldn't win. So we'd say, hey, you got to be the hammer, not the nail, the hammer. You got to be the hitter, not the hittee. Well, what we were telling them to do really is to compensate. If they have less mass, all right, they need to compensate by increasing their velocity. So when they're tackling, they need to be moving in. And as they're moving in, they're getting more velocity. So even if their mass can't be increased, their velocity can, and they can have more momentum for that collision and for that tackle. Okay, so that was it for freshman football. A quick service announcement. Never, ever, ever cut off a truck. All right, so think about, let's say you're pulling off the highway and you see the exit and you're gonna, I gotta get off that exit, and you pull off. Do never cut off a big truck that might be gonna be behind you. That big truck or big bus or whatever has a whole lot more momentum. It has a whole lot more mass, and it's going to need a bigger stopping distance because it has a lot of momentum. So never cut off just because you're a small little car and can't get in there. Don't. All right, moving on. Mass times velocity, all that is good. And yes, on a test, I could ask you, what's the momentum of this? What's the momentum of that? Or, hey, what has more momentum, this or that? And yes, I will. I'll ask you some questions like that on tests. But far more important than that will be this idea of conservation of momentum. Okay, and conservation of momentum is that the law will say that the total momentum before a collision, event, whatever, is going to be equal to the total momentum after. And that seems kind of boring, but it's going to be very, very powerful. Because what it means is that if I know the total momentum before something happens, I right away know the total momentum after something happens. And then I can solve for what changes and know what happened. And we're going to talk about how even the police use it a lot. But the formula, here's a quick formula to look at. All right, P1 plus P2 is equal to P1 prime plus P2 primed. What does that mean? Well, P again just means momentum. So let's say I'm about to tackle somebody, okay? So I'm going to say that I'm number one, all right? My momentum is number one. The other person's momentum, that person's momentum is going to be number two. So before we collide, the left-hand side of any equation with momentum will be before. The right-hand side of any equation will be after. So my momentum plus the other person's momentum, if you add those two numbers together, that would be my total before. So let's say I'm running at that person and let's make up a random number that isn't actually accurate, but let's just say I have a momentum of 5 as I'm running towards that person. And let's say that person is sitting still. What's that person's momentum going to be? It's going to be 0, right? Because it's not moving, the velocity is 0. P2 would be 0. So we could say the total momentum before is 5 plus 0, or 5. So now let's say after. Let's say I collide. I stick my elbows out and I knock that person out. I bump into that person and I slow down. And let's just make up a random number and say that after I collide, I have a momentum of 2. Okay, well then how much momentum does the other person have to be? Well, the total before has to be equal to the total after. So that means that person's momentum has to be 3. Because 2 plus 3 has to add up to the original total of 5 before. Okay, now, what about those tick marks? Those little apostrophes just mean I'm still describing the same person as before, and it's going to be their momentum, but I'm going to put a little tick mark to say after. The number has changed. So P1 was my momentum before. P1 primed, the P1 with a little tick mark, means my momentum after. I still am describing me. I'm still talking about momentum, the letter P. I'm still talking about me, number 1. But there's going to be a little tick mark to say the number in there is different. Okay. Now, there's no real actual momentum guns to measure. We don't measure momentum by itself. We have to measure mass and velocity. So what we actually have to do is break it down into a mass and a velocity. So this P plus P, we'll do that, just to get a general idea of it. But really, we have to substitute in what M, or what momentum is, which is mass times velocity. So we substitute in underneath M1 V1 plus M2 V2, okay, is equal to M1 V1 prime plus M2 V2 prime, okay? And this formula is really what's going to be useful. I could talk about a car colliding and figure out what the velocity is before by figuring out what the velocity was after, okay? Now again, notice that my mass really won't change. It's not like I'm going to run and my leg falls off after a collision. So the tick marks are going to go with the velocity. So M1 on the left side is going to be the same as M1 on the right side. However, V1 on the left side would be some value V1 primed, that's where we put the tick mark, is going to be a different number, but still describing the velocity of me, person number 1. All right. That formula looks ugly, but it's going to get really easy. And you really, with this stuff here, momentum, it's going to be basic algebra. There's just going to be one variable you're going to have to solve for. Okay. Now, Let's take it a step further. So here we go. There are actually three different types of events that could happen with collisions. You could have two objects collide and bounce off each other. You could have two objects collide and stick together, or you could have the opposite of it. You could have two objects that are stuck together and then they separate. This will be called elastic collisions. This will be called inelastic collisions. And the last one is recoil. Okay, so let's talk first about elastic. With elastic collisions, momentum will be conserved. And with every type of event, elastic, inelastic, or recoil, momentum will be conserved. The left-hand side will always have to be equal to the right-hand side. With elastic, however, energy is also conserved. Okay, if you need to try to remember it somehow, elastic, E is for energy. Energy is conserved. Energy is going to be saved in elastic collisions. Okay, and another thing to remember with elastic collisions, our objects are going to bounce off. They were separate before. They're separate afterwards. They bounce off. So elastic collisions, think about elastic bands are also called what? Rubber bands. So in an elastic collision, they will bounce. Rubber bounces, elastic collisions bounce. Okay, now, inelastic is going to be still, momentum still has to be conserved, but with inelastic, instead of bouncing off, they're going to stick together, okay? But energy will also be lost. So think about if any of you have been in a car accident, hopefully it hasn't been bad, but if you've been in a car accident and has anyone felt the bumper where the dent has been in your car? And you'd notice something. If you feel that bumper, it is hot because your car had energy. Your car was moving along. It had kinetic energy, right? You were moving, you have a velocity, you had kinetic energy. All of a sudden you collide with another object, you are going to lose energy. And that energy will be lost to heat. So with inelastic collisions, energy will be lost. Okay? So inelastic, objects stick together, and energy will be lost to heat. All right, now the third one is going to be recoil. And I'm sorry, you know what, and I don't even have a slide for recoil. I'm going to show you the three equations. Now, before you start copying down these equations, before you start freaking out and thinking that these equations are all crazy looking, I want you to actually look at these equations. I'm going to explain them, but I want you to look at them like they're pictures, okay? Not equations just yet, but just pretend they're pictures. All right, here we go. The first one, we already saw this one, elastic. Now notice with elastic collisions, you have two objects that are separate. You have M1, V1, and M2, V2, and they're separated by a plus sign, okay? They're separated apart. After the collision, so the left-hand side is before, the right-hand side is after the collision, they're still separate, okay? They're still, the M and the V's are still separate from each other. M1, V1 primed is separate from M2, V2 primed. All right, now, the next equation, inelastic. Left-hand side before, they're separate, right? They're separate, and then they stick together. So, inelastic, you're separate before, but then after, they're going to get stuck together. So if you look at the left-hand side of inelastic, they're stuck together by the two parentheses. The M1 and the M2 are stuck together by that parentheses, okay? Now, another way, for all you math nerds, you can think of it this way. If two objects are stuck together, they have to have the same velocity, okay? So if the velocity is the same number, if they're stuck together and they have the same velocity, if that number is the same, well, then you could factor it out. And so the parentheses are factoring out the velocity, all right? But that's only for you math nerds. Everyone else, you can start paying attention again. Okay, finally, you have recoil. And recoil is the opposite of inelastic, because now recoil, something moving along and then separates, okay? And you could think of it, recoil, if anyone's ever fired a gun, okay? A gun is going to have recoil. The gun and the bullet are stuck together before, and when it's fired, the bullet's going to go one way. You have to have recoil. You have to have the gun go the other way because momentum has to be conserved. There's no way that you could fire a gun and the bullet goes one way and the gun just stays there, okay? Now, the bullet is much, much lighter, has a much smaller mass, So it has a really high velocity, but a very small mass. The gun, on the other hand, is going to have a really, really big mass compared to the bullet. Okay, so it's going to have a much smaller velocity, but it still has to move. All right, could be the same thing throwing a basket or a basketball. If I throw a basketball, the ball is going to go one way. I am going to have to go back a little bit because of recoil. Okay, but looking at it in terms of an equation, you have they're stuck together before, so those two parentheses are holding masses together before, and then M1V1 and M2V2 are separated afterwards. Okay, so it's the same equation as the inelastic, but they're flipped. And again, we flip them, and because we always want the left-hand side to be equal or before, and the right-hand side to be afterwards. Okay, you can also look at, then you can start looking at them in terms of equations. I'll say with recoil, most of the time, recoil, the objects are sitting still beforehand. So a cannon is about to fire a cannonball. Well, the cannon and the cannonball are usually going to be sitting still at first, so their velocities will be 0. So that velocity on the left-hand side that they share usually are 0. Okay, not all the time, but usually. All right, let's do a couple more examples, and let me just explain a few examples of momentum for you. Okay, so how about pool? The next time, if you've ever played pool, if you want to get a good break at the beginning, okay, so somebody racks up the pool balls and you're going to make that big break. You don't want to embarrass yourself, right? So when you break, don't break with just your arm, okay? You don't have that much mass in your arm. So if you just try breaking with only your arm, there's not a lot of momentum behind that break, which means the balls won't separate as much. So what you want to do is get your body into it. You want to step into that break, and if you step into that break, your whole body is now moving, your whole mass, okay? So you have a whole lot more mass than, even these massive arms like this, right? But if I have my whole body behind it, I'm going to have much more mass behind it, which means I'm going to get much more mass or much more momentum into that cue ball, which means there's much more momentum going to the break, and the balls will break further. Okay, so there you go. How to play better pool. You're welcome. All right. The next time you're in a bar fight, just kidding. But boxers do not punch with just their arms. Okay, boxers are not going to punch like this, because again, even if you have big arms like these, that's not a lot of mass, which means there's not a lot of momentum. So a boxer is going to step into the punch. He's not going to be punching like this. He's going to get his whole body behind that punch, which means now he has all the mass, or she has all the mass that's going to transfer to momentum to transfer to that person's face. There you go. All right. This example, just take from my example. Okay, trust me. Do not play baseball with a semi-deflated basketball. It was 7th grade. My friends and I were outside playing in the street, hitting baseballs and tennis balls, and one of my friends decides to throw a semi or half deflated basketball at me, and I have the aluminum bat. It comes up, I swing, and you're thinking, if it's a tennis ball, I swing, I hit that ball goes flying out. Well, I take a swing of that basketball. The basketball stays right there in the air, and the bat comes flying back in my face. Okay, what happened was all of that momentum, because the basketball has so much more mass, all of its momentum transferred to this light aluminum bat. So instead of the bat following through, the bat went straight back at my face and gave me a nice big black eye. So there you go. Just learn from me. All right. And that is it. And I'll talk to, and I'll try to show a demonstration later about basketballs and golf balls and all that stuff. But that is it for me. And I hope you enjoyed it. Thanks.